All right, yeah, so thanks everyone for coming, either in person or virtually. I see a lot of people are on Zoom today. So yeah, I guess today we're going to be continuing the talk from last time, and today the focus will be on discussing these applications to proving lower bounds for locally decodable and correctable codes, that is error correcting codes with certain local properties. And the main technical tool we're going to be using are again these induced subgraphs of Cayley. Okay, and this talk is again based on joint work of my 5 co-authors, Omar, Venkat, Tim, Oliver, and Pravesh. So in case you've forgotten what we did last time, let me just give you a brief summary. So last time we said we had some method for solving combinatorial problems if we could reduce them to understanding some family of sparse linear equations over some finite field such as F2. And then the way we analyze the system of linear equations is by understanding spectral properties of these induced subgraphs of Cayley graphs. And this had the feature that if the pointer not work, oh, it's too bad. Okay, so this reduction had the feature that we could understand this family of linear equations, we could prove results about the combinatorial problem. And so then we did that by using these spectral tools. Okay, and the typical use case here was that we'd reduce the problem from unsatisfiability of some linear equations that were random-ish in some sense, and then we would show unsatisfiability using the spectral methods. And if you recall the 2 problems from last time, one of them was this refutation question, where the problem, as I defined it, was quite literally to argue number 2, doing this via an algorithm. So the algorithm itself was to compute these eigenvectors and eigenvalues of these Cayley graphs. Technically, I stated that problem for systems of linear equations. I could have stated it for systems of nonlinear equations, in which case there would have been some reduction from the nonlinear case to the linear case, but I kind of swept that under the rug. And then the other problem I discussed was this problem of finding short linear dependencies among sparse vectors over F2, or finding these short even covers in hypergraphs. And there we reduced the problem to showing unsatisfiability of some system of linear equations that we secretly knew was satisfiable. And then we argued unsatisfiability under the condition that there was no short linear dependence. Okay, and you may recall from the talk last time, I called these induced subgraphs of Cayley graphs Kikuchi graphs, and that's because there's some connection in statistical physics with this notion of Kikuchi free energy. And this was a connection made by the original work of Wine, Lowy, and Moore that defined these matrices and used them to give an algorithm for tensor PCA. Okay. And just to again finish the recap from last time, I mentioned that there were 4 main applications we had. The first was proving this optimal girth versus density trade-off for hypergraphs. The second was giving this algorithm for refuting smooth instances of constraint satisfaction problems. These were the 2 problems I discussed at length in the previous talk, so we're not going to talk about them today. What we're going to talk about today are the other 2 applications, which are proving lower bounds for locally decodable codes. This has some interesting application to showing existence of k-term arithmetic progressions in dense subsets of the integers where the common differences are some random restricted set. And then we can also prove exponential lower bounds for locally correctable codes. And this has an application to proving Hamada's conjecture for 4 designs over fields of characteristic 2. Okay, so last time we talked about the first 2 problems. This time we're going to focus on items 3 and 4, which are the coding theory applications. So the plan for the talk is going to be roughly the same format as last time. Okay. In the first part, I'm going to tell you about these 2 codes, locally decodable and locally correctable codes. And then I'm going to tell you about the history of these problems and the results that we have. And then we'll go to a break. And then after the break, I'll give you some proofs on the board. Okay. So same format as last time. So yeah, I guess I'll just get started with defining these codes, and to start off, I'll define locally decodable codes. Okay, so there's 2 ways to define locally decodable codes. There's what I'm going to call the semantic definition, which will make the name or make the reason for why we call these codes locally decodable codes rather obvious. And the other is the combinatorial definition, which will perhaps give you a better understanding of what these codes actually look like, but will not be so obvious why they're locally decodable. Okay, now I'm going to break with perhaps the standard convention. I'm going to define the combinatorial one first, and then I'm going to relate it to the semantic definition. So what's the combinatorial definition? Well, I'm going to define a Q-query locally decodable code to be a collection of Q uniform hypergraphs, H1 through HK, where if you recall from last time, a Q uniform hypergraph is simply a collection of sets that are subsets of some vertex n, where each set has size exactly q. So a 2 uniform hypergraph is just a graph because, well, if you have subsets of vertices of size 2, those just are your edges in your graph. And a hypergraph is a generalization of this to sets of size q. And here think of q as a small constant, like maybe 3 or 4 or something like this. Okay, so unlike the problems I defined in last week's talk, here the hypergraphs now have some structure. So I give you k of them, but each one of these hypergraphs, h sub I, is a matching. And it has size delta n, meaning it has delta n hyperedges. And think of delta as some small constant, again, like maybe 1 over 100 or something like this. So what does it mean for a hypergraph to be a matching? Well, a matching in a graph is simply a collection of edges where no two edges share a vertex. That is, the edge sets are disjoint. So here, the hyperedges are disjointed. So just a generalization of the graph definition to hypergraphs. Okay. So I give you these k hypergraph matchings. All right. I mean, I can always come up with k hypergraph matchings, so they need to have some property. And the property is the following. I want to pick any b in 0, 1 to the k, any vector b, and I'm going to define for b a system of inhomogeneous linear equations via these matchings. Okay, so the variables are x1 through xn, the field I'm working over is f2, and the equations look like this. For each hyperedge c that lies in the hypergraph h sub I have the equation sum of v and c, x and v, is equal to b sub I. Okay, so these equations are q sparse because the left-hand side of each equation has q variables in it. And you can think of the hypergraphs as telling me what the right-hand side of each equation should be. So I've just sort of taken a normal system of linear equations and I've broken the hyperedges up into these sets, which group them by the right-hand side. So every hyperedge in h sub I gets the right-hand side b sub I. Okay, and the condition I want is that this system of linear equations is satisfiable for every choice of b. Now let me point out that the number of equations here is, well, I have delta n hyperedges per matching and I have k of them, so I have delta n k equations. K we're going to want to be super constant, so something that's a function of n. Delta is a constant, so this is many, many more than n equations. So in general, if you pick arbitrary matchings, the system of equations will be unsatisfiable. So the fact that the system of equations is satisfiable for all b is very, very special. This is not a typical property that typical matchings would have. It means that there's some very nice special structure that these matchings have that makes these equations satisfiable. Okay, so there's something special going on because I've given you a lot of equations. Now, you might be scratching your head and thinking, hey, Peter, where's the code? This is not how I like thinking of error correcting codes. An error correcting code should take a message. It should encode it in some way. And then I think about transmitting your code word over some noisy channel. It gets corrupted. You want to recover the message from the corrupted string and so on. This doesn't really look like a code. So what's the code? Well, right, so typically we think of the code as being this defined by some way that we encode messages. Here the message length is k. K, by the way, is the same k up here. So given these matchings h1 through hk, I can define my encoding map by encoding b via some solution to the system of linear equations. In fact, you can pick the solutions in some careful way by not picking an arbitrary solution for each choice of b, picking them in a way that depends, so it's kind of consistent across the different choices of b, so that this encoding map is f2 linear. That means, remember, 0, 1 to the k, I can think of as f2 to the k, it's just a vector space, and same with 0, 1 to the n. And so this encoding map is some injective map from 0, 1 to the k. And that means that the image of the map, the code words, are just a vector space of dimension k in f2 to the n.
Worried that I was talking, but we didn't hear anything.
Oh.
All right.
Maybe, I mean, if you can type in the chat if he wants to talk,
Yeah,
we're
I
able to hear
texted
him.
him, so hopefully.
Okay. Okay, so what's the goal here? Right, I've defined some problem, and the goal here is we want to make k as large as possible. I can clearly, put one matching in if here I want to pack in k of them where k is somewhat large. And so I can tell you, I fix n and fix q, the size of my hyperedges, and I want to ask how many matchings can I pack in so that the system of equations will always be satisfiable, right? Equivalently, you can think of k and q as being fixed, and then you want to minimize n as a function of k and q. These are both the same problem. Okay, so this is the definition of a locally decodable code. What I want to do now is connect this to this even cover problem that I talked about last time. So this is the definition of an LDC. And as the title of the talk said, we're going to be eventually proving lower bounds for these codes. What that means is I want to establish a condition for when H1 through Hk are actually not a locally decodable code. And this is pretty straightforward. I can read off the definition and say they're not a locally decodable code if and only if there is some B that will make the system unsatisfiable. Okay, fine. I mean, I didn't really do anything here. So let's unpack this second condition here. When does there exist some B such that size of B is unsatisfiable? And we can do this by understanding some very nice combinatorial condition on these matchings. So I claim that there exists a B such that size of B is unsatisfiable if and only if I can find hyperedges C1 through CR that are in the union of these matchings, okay, such that they have the following two properties. The first property is that they form an even cover. This just means that when I take the symmetric difference of these sets, I get the empty set. Equivalently, if I sum up the indicator vectors of these sets mod 2, I get 0. Or another way to phrase this is that every vertex V in N appears in an even number of these guys. Okay, so that's the first condition. The second condition is that there's some color I where I think of the hyperedges as having colors where the hyperedges in the matching H sub I have color I. So there's K colors. And I look at the sequence of colors that appear in this even cover. And I want some I to appear an odd number of times in that sequence. So why does this show that the equations are unsatisfied? Well, what I'm going to do is I'm going to sum up the equations corresponding to this even cover. The first condition, that it's an even cover, says that when I sum it up, the left-hand sides of the equations all drop out, they all cancel, because each V appears in an even number of things. So X sub V will just cancel with itself, and we get 0 on the left. The second condition says that some I appears an odd number of times, which means when I sum up the equations on the right, some B sub I is still there. It doesn't cancel. And so then I can set that B sub I to be 1, all other B sub j's to be 0, and I get the equation 0 equals 1. So therefore I cannot satisfy the system of equations. I've got a contradiction. Okay, and this is equivalent to there being a solution for every B. Okay. So if you remember this hypergraph Moore bound I defined last week, this should feel like a very related problem. It's really some sort of rainbow or colored variant of this even cover problem I discussed last time. Here the question is to find an odd colored even cover, where odd color is just this condition that some color appears an odd number of times. There's a variant you could call the rainbow even cover problem, where you want the colors to be rainbow, meaning each color appears at most once. Clearly, if I can find a rainbow even cover, I can find an odd colored even cover, but the converse is not necessarily true. So to just rephrase this, the task of proving a lower bound showing that K is bounded by some function of N and Q is equivalent to proving the extremal combinatoric statement that any collection of F of N cubed matchings has some odd colored even cover. Okay, so these are the equivalent statements. You can think of finding the optimal K for locally decodable codes as just trying to determine the extremal threshold of this combinatorial problem. Okay. So this is the combinatorial viewpoint on locally decodable codes. I do want to give you briefly the semantic definition so you can see why these codes are actually called locally decodable codes, and then I'll connect the two. So the semantic definition is going to look at this viewpoint where we have an encoding map. So I think of my message B in 0, 1 to the K, and then I want to encode it into a length n bit string X. And then, as is typical with error correcting codes, we're going to let some adversary come in and introduce an arbitrary delta n or gamma n errors into the string X that produces this corrupted string X tilde. So this is the standard setting of error correcting codes. Typically, we then want to be able to recover B given X tilde. Now, the special property that a locally decodable code will have is that we want to be able to recover any particular bit of B while only reading a small number of bits of X tilde, the corrupted string. And so formally, this means there's some decoding algorithm. We tell it, what bit are we trying to decode? We tell it the index I. The decoder then will be randomized, so it tosses some coins and then decides what Q indices of X tilde to read. This is the same Q as the arity of the hyperedges. And then it outputs some B hat sub I. Okay, And we would like the decoder to output the correct bit B sub I with probability, say 0.99, when there's only at most gamma n errors, and we want it to be able to do this for any choice of the index I that I decide.
I have to say that in this perspective, it's clear that if you don't care about reading a constant number of bits, you are allowing yourself to read anything you want, then you can do this.
Yeah, well, I mean, if you're allowed to read like n bits,
N bits.
you can
or
read the
half
whole
an
string and there's no localness.
Right.
Yes.
But on the other hand, in the combinatorial point of view, you're starting to tell me about these hypergraphs and you want an even cover. It's not so clear that you can do it.
Yeah, though there I restricted the hypergraph edges to have uniformity Q, which,
But I'm saying, suppose you tell me now, look at that same problem, but now I don't restrict them to be matchings and I don't
Yeah.
restrict them to be Q uniform. I still don't know if it makes it easier. Whereas here it's clear that it makes it easier.
I guess you're kind of right. I mean, you could just say that you're looking at any linear dependence and then you have like n+1 equations. There's probably some simple thing you can do with the fact that the dimension is n. So if I give you arity n, you can just kind of do anything. But yeah, I mean, you're kind of right that it's a lot more obvious what's going on in terms of like the query version. I'm going to call Q the number of queries, by the way, which is really the uniformity of the hyper edges, but the queries are because the decoder is asking questions and making queries and getting back answers. Right, so this is the semantic definition. Let me just briefly connect the two. I'm going to show that the combinatorial one implies the semantic definition. The reverse direction is also true, but requires more effort, so I'm not going to do it in the talk. So I've given you these hypergraphs H1 through HK. That's the combinatorial definition. That's what you get from it. And I have to tell you what the operation of the decoder should be when I tell it to decode the ith bit. And the answer is it's going to use the ith hypergraph H sub I to decode the ith bit. So what's it going to do? Okay, it's going to pick a uniformly random hyperedge. It's going to read the bits on that hyperedge, and it's going to output the sum of the bits that it reads. So it's pretty straightforward. The tricky thing is the following claim, which is that if there's at most delta n over 100 errors, then this actually outputs the correct bit with probability, say, 0.99. So let's see why I picked delta n over 100. That's because there are delta n hyperedges. So if I have delta n over 100 errors, at most 1 over 100 fraction of the hyperedges can even have an error in them. So the claim I'm going to now make is that if I read a hyperedge that has no errors, I get the right bit out. And the reason for that is that at this point, I'm outputting the sum of v and c of x sub v. Now, by that system of linear equations, that's equal to b sub I. So then I get the right bit out. And I get it out with probability 0.99 because that's the probability that I get a clean hyperedge that has no errors in it. Okay.
Peter, you did not define the encoding function.
Yeah, I emailed him and texted him.
Because I can't hear him.
He's not listening either, so I guess it's maybe you should say, Avi, we cannot.
Okay,
hear you.
Avi, we cannot hear you. So if you are trying to say something, type in the chat, please, and Arik will read it.
You cannot hear me?
Because I don't have.
Or text Arik, sorry.
Okay.
Okay, so this is the semantic definition. I've connected it to the combinatorial definition. So hopefully you have some idea now why these are called locally decodable codes. It's because we're locally decoding the bits of the message kind of done. Okay. Now there's a reason that we actually study these objects, besides the fact that their combinatorial characterization is perhaps also on its own a nice problem. And that's because these are really influential objects in the history of theoretical computer science. Their two most notable applications are to probabilistically checkable proofs and the proof of the PCP theorem and complexity theory, and also private information retrieval and cryptography. And these are both fairly fundamental objects in both these areas in complexity theory and cryptography, which is why these codes have received a lot of attention. They also have plenty of other applications that are also very interesting, but those two, PCPs and PIR, are the two main ones. Okay.
Oh, I have something from Avi that you didn't define the encoding function for the reduction.
Oh, for the reduction? The encoding function is the one where the encoding of B is just any solution to that system of linear equations. Yeah, it was what I had like 2 slides ago.
Right.
Yeah, that's true. Yeah, it's the same encoding function. That was exactly. Okay. So if anyone was confused, hopefully that clears things up. Yeah, so that's locally decodable codes. Now, I also have to tell you about locally correctable codes. And the nice thing about this is because the names sound very similar, locally decodable and locally correctable, you can guess that the definitions are going to be very similar. So I'm going to be able to reuse a lot of what I just told you about for locally decodable codes, and I'll map it onto this new definition. So as before, there's the semantic and the combinatorial definition. As before, I'll give you the combinatorial one first. And as before, I'm going to give you hypergraph matchings. The difference here is I'm giving you now n of them rather than just k of them. So I'm giving you more matchings. Okay. And the condition or system of linear equations is going to look a little bit different. I'm going to give you a system of homogeneous linear equations where the equations now look like this. For each u and n and each c and h sub u, I want the sum of v and c of x sub v to be equal to x sub u, or equivalently, I can move x sub u over to the left as I've done here, and I want the sum of these things here to be 0. So this is a system of q plus 1 sparse linear equations because I have q from here and then the extra 1. Okay. I also give you delta n squared of them because I have delta n hypergraphs and then n matchings. Or sorry, delta n is the size of each hypergraph and I have n of them. Okay. And what I want is for this system to have a solution space of dimension k. And k I want to be somewhat large, so I want this to have a non-trivially large solution space. Okay, again, I give you a lot of equations. So if I pick random matchings, the solution space will have dimension 0. It'll just be the all zeros vector. So I want there to be a lot of non-trivial solutions here.
Maybe just to say, so
Yeah.
you have a solution space of dimension k, even that doesn't completely specify the encoding because you can change basis on the 2 to the
Exactly.
k.
So this is the next
It's
point.
coming.
It's
okay.
coming. This is all coming. Don't worry. Yeah. So again, we wanted to think of our encoding map. I can pick any linear map between 0, 1 to the k and solutions. And again, my goal is to maximize k as a function of n and q, or equivalently, if I tell you the target dimension k, I want you to minimize n. Now, as Arid is pointing out, I can choose what basis to do this map. And a key observation is I can pick a rather nice basis. By permuting the hypergraphs h1 through hn and so on, I could choose a basis so that the encoding of b restricted to the first k bits is just literally b. So that is, this transformation is the identity on the first k bits, and then it's got extra stuff, right? And if I do this, this makes it pretty obvious now that a locally correctable code is locally decodable. I just pick the first k matchings, and for those k matchings, when u is in k, x sub u is just equal to b sub u. So then I recover the system of linear equations that I had before. Okay. Is that clear? Okay, so again, I can try to connect this like I did here, just an even cover problem, but I can do the same for locally correctable codes. And the answer is I can define some matrix M, where the rows of the matrix are just these q plus 1 sparse equations. This is sometimes called a parity check matrix. And the message length k is the dimension of the kernel of this matrix. So proving a lower bound that k is less than f of n just shows that any n matchings must have the dimension of the kernel of the matrix less than f of n q. Okay. So in locally decodable codes, we wanted to prove some threshold for the f of n for when there exists an odd colored even cover. Here we want to bound the dimension of the kernel of a matrix that looks like this.
Peter?
Okay. I think obvious.
Yeah, for people who don't read, don't you want to show that?
Doesn't want to have Hamming code as an example of a 3-query LDC, the Hadamard code.
We're getting there. We're
We're
getting there.
getting there, yes.
Yeah. So first I'm going to tell you the semantic definition of locally correctable. Yeah. Javi keeps jumping the gun.
Oh, even for locally decodable codes,
Yeah.
we could have done, it, right?
Yeah. Well, you'll see it in a second. I wanted to get to the definitions first and then show you.
So such a thing exists.
Yeah, so these things, we'll see it. Yeah, exactly. So the semantic definition is going to be very similar. The difference is now, instead of the decoder trying to decode bits of the message B, it takes as input a U and N, which specifies which bit of the uncorrupted encoded string X we want to recover. So that's why we get N matchings rather than just K of them. Before we got K matchings, which are the ways we decode the bits of the message. Here we get N matchings, which is the way we decode the bits of the encoded string X. Okay? So that's really the only difference. The same connection between the combinatorial and semantic definition still works. And this choice of basis that I told you about means that the encoding map has first k bits that are actually equal to b. And so this immediately makes it obvious that a locally correctable code is locally decodable because we can correct any bit of the encoding. And in particular, we can correct the first k bits, which are just the message. Okay, so that's the connection there. And again, the question for both of these codes is to find the optimal length n as a function of k and q, or equivalently find the largest k as a function of n and q. Okay, and I do want to point out that, as I said, these systems of linear equations have many more than n equations. So if I just pick something like a random code, it's not going to satisfy these guarantees. So showing the existence of even a single code requires some non-trivial amount of effort, because the standard way to show existence of an error correcting code is to just pick a random one and argue it satisfies the conditions we want with high probability. And this is not going to be true here. But as Avi points out, there do exist these codes. They're not actually too hard to construct. So Reed-Muller codes are locally correctable and therefore also locally decodable. These are some of the oldest error correcting codes that were ever constructed. And they keep a block length n that's exponential in k, so it's like 2 to the k to the 1 over q minus 1, where q is the number of queries. So let me just give you this example for 3 queries. So the code words we're going to think of as being degree 2 polynomials in some large number of variables t over some small finite field. Let's just pick f4 as an example. And so the code words, the way we encode a polynomial is we evaluate it at every point in this domain. So let me now tell you the parameters of the code. The message length, or k, is the dimension of this subspace, which is the number of coefficients in this polynomial g. This polynomial has roughly t squared over 2 coefficients. The encoding length is the number of evaluation points that I pick, which is 4 to the t, because I have working over f4 to the t. Okay. So I can rearrange, put the encoding length in terms of the message, and I get something like 2 to some constant times the square root k. Right? So I now need to tell you what these matchings are, or equivalently, I need to tell you how to decode g at a particular point z. And to decode g of z, it's again pretty straightforward. I just pass a random line through z. We're working over f4, so the line has 4 points on it. One of them is z. I don't want to read z. I'm going to read the other 3 points on the line. And yeah, so I read the other 3 points of the line. I get the restriction of a degree 2 polynomial to a line, which is also a degree 2 polynomial. I know its evaluations at 3 points, so therefore by polynomial interpolation, I can recover its value in g of z as well. Okay, so let me put this in the combinatorial definition using these matchings. And the answer is that the matching h sub z for the point z is simply the set of triples that form points such that the 4 tuple is a line. Okay. This is sometimes called an affine geometric design theory, and that's really what's going on here.
Can I ask why it's over f4? Is there any special thing about f4 between?
Yeah, because otherwise you have a degree 2 polynomial over f2.
Oh,
That's
okay,
kind of
okay,
weird.
it's not
Yeah,
that.
so I want my field size to be like a little bit larger. You can though recover a binary code by just applying the trace map. So like the f4 is not so important. I can get back to a binary code if you really care about f2.
I mean, a more basic example is when you look at degree 1 polynomials, linear functions over f2, then you have a 2 query LCC.
Yes.
If you want to read a linear function at a point y, you read it at a point x and at a point x plus 1.
Yeah, so this is a more sophisticated example. I feel like Hadamard code's too simple.
What?
Hadamard code's too simple. Actually, there's a reason I'm giving you this example, but there will be a reason for it later. Okay, so the question I want to ask is, can we do better than Reed-Muller codes? Okay, so give us some family of codes. I mean, I gave you the example for q equals 3, but you can imagine for larger q, I picked degree q minus 1 polynomials, and it all works out. Okay.
Even the Hadamard code is kind of cool.
I mean, sure. I do agree, it is cool. But I mean, this example, I think, shows what's a higher degree greater than 1, which makes it clear how to generalize.
Yeah.
To larger queries.
Yeah.
Right. Hadamard code feels very specific to q equals 2.
Yeah, you don't necessarily know how to generalize it when you see it. That's
Pick this example for a reason.
just trying to bug you a little bit.
Okay, so one thing I do want to say is we actually can do better, slightly. which is that if I look at the dimension of the kernel of the matrix formed by these matchings, it's actually a bit larger than t squared over 2. And this is a very interesting fact. It's actually about t squared. So the length here is actually 2 to the 2 root k, not 2 to the 2 root 2k. Okay. So you can do slightly better, but what I mean by can we do better is I want to get more than a constant factor improvement in the exponent. Okay, I want to get something a bit better than that. So this is a simple example. Let me now tell you all that we know about locally decodable codes, at least the extent of our knowledge up into the year 2022. Okay, so we have this example and we want to know if we can do better. So I could try probing this by picking various values of q and seeing for like, q equals 1, can we do better? Q equals 1, you can't do anything with one query. If you stare at this for a little bit, you'll realize you can't really do anything with one query. So we got to go to q equals 2. And Arit's favorite code, the Hadamard code, achieves a block length n that's 2 to the k. It's a 2-query code. Its encoding length is very bad, okay, because it's exponential in k. This feels very, very inefficient, but it's tight. So here we can prove a matching lower bound that shows that up to a constant factor in the exponent, this is a tight lower. This is the optimal code. Okay, so we solved the case for q equals 2. So what do you do next? Increase by 1 and go to q equals 3. So here I said we had this code that achieves a length n is 2 to the 2 root k. And here's something very interesting happens, which is that there is a construction called matching vector codes by these works of Sergey Yakanin and Klim Efremenko that achieve a block length that's 2 to the k to the little o of 1. Compare the exponents here, that's k to the 1/2, k to the little o of 1. So this is a much, much better code, much more efficient encoder. Okay. Okay, now we got a better code. You can ask, is this the best we can do? So we can try to again prove lower bounds. The answer is that we have absolutely no clue. Our best lower bound is n is at least some k squared, 3LDC lower bound from this work of Karanidis and de Wolf. Now, not only is this polynomial in k, which is very far away from the construction, it's a small polynomial. Even getting like k to the 2.1 is something that we don't know how to do. And more generally for other q, we get something that's k to the q over q minus 2 for even q. And for odd q, we do the sensible thing and we give up because odd q is hard, as I mentioned last week many times. And we just pretend that if q is odd, q plus 1 is even, and I apply the even query lower bound. And that's it.
By the way, in a few weeks, I don't remember when exactly, we will get a lecture by Swasti Koparty where they have some improvement. They have some general way to view the matching vector code. And I don't do you remember their improvement?
I think they just sort of generalized it to all queries. I did see the paper a long time ago.
Yeah, I also.
Or not a long time
but we
ago,
will
but like a few
see.
months ago when it came out, yeah.
Yeah.
I think it was just some generalization that kind of got codes that look like this, but for a wider parameter regime than what was initially shown.
Well, there's also something mysterious about that construction. Maybe they demystify it
I
somehow.
don't think it's that, okay, I don't know, I've looked at it a lot, I don't feel like it's that mysterious anymore.
It's
but
mysterious.
Fine. It's mysterious.
Wait, sorry, what is the block length for matching vector code is n at most 2 to the k to the what?
Little o of 1.
Little o.
It's 2 to the 2 to the root log k log k, if you care about the actual. So the exponent's 2 to the root log k, basically.
That's already mysterious. Come on.
Yeah.
I don't know. Okay, sure. I mean, everything's mysterious till you understand it.
That's
Okay, so the other point I want to make is there's actually some evidence that going beyond k squared is rather hard. There have been some works on investigating why we are stuck at k squared, and they've come up with some reasons why our techniques are not going beyond this k squared bound.
You mean lower bound?
The lower bound, yeah. So proving the lower bound. So that was the story in 2022. Of course, it's not 2022 anymore, it's 2025. And so let me tell you about our 2 results for locally decodable codes. The first is we prove a cubic lower bound for 3 queries. Okay, so this goes beyond the k squared bound, goes beyond that k squared barrier. The thing to notice is that here, if you substitute in q equals 3 in the even query trade-off, you get k cubed. That's where it's coming from. So we're proving this k to the q over q minus 2 lower bound for this particular odd value of q. And the interesting thing is extending this to all odd q didn't work. We got stuck somewhere in the proof and we were unable to make the approach work. And that was the state of affairs until very recently, just a couple months ago. Oliver and I proved the lower bound that gets this k to the q over q minus 2 for all odd Q. And there was a concurrent work of Basu, Shea, Lin, and Kotari. This is Arpan Basu and Andrew Lin. These are both PhD students at Princeton. Of course, Pravesh is also at Princeton, and Tim's another one of his students. And they proved essentially the same result. The result, I guess, technically has a slightly weaker polylog factor hidden in the tilde, this omega tilde 1, but like the main thing here is to get the k to the q over q minus 2. That's the polynomial factor. So really, it's essentially the same bound. And so today, after the break, the main thing I'm going to show you is again the proof for even q. I'm always going to do even unless I absolutely have to do odd, because you kind of see there's a reason that even q is somehow technically easier to do than the odd q. All right.
And do you think that exhausts the Kikuchi approach to this?
The naive approach, yes, but I think there's more you can do. It's just the naive bound. You'll see this when I go on the board. There's some naive heuristic we can compute that will predict what lower bound we can get if we do something very straightforward without trying to do anything terribly clever. And then this is the k to the q or q minus 2 is the threshold that's predicted there.
In terms of techniques, can you comment on the combination between your work and the association of
Yeah, I mean, essentially this Kikuchi approach seems like it can prove this bound, but there's some technical part in the proof where you get stuck, which is when these hypergraphs through HK have some correlations between each other, and you have to handle that. We came up with a very slick way of doing it, where typically what you do for odd queries is you take two hyperedges that share a vertex and you like link them together to cancel that middle vertex and derive a new constraint. We found out a way to make a bipartite version of the graph that will essentially handle all the irregularities in kind of one clean shot without needing to do anything too complicated. The normal way to handle this decomposition step is that if, when you do this derived thing, you might still get hyperedges that look not very regular or have like pairs of vertices or something that appear together many, many times, more than you would expect. And when you do that, it typically means that you should be canceling maybe two variables instead of one at that first step. The problem in this problem is that it actually doesn't work. That proof strategy, which is what we actually did in the odd case for the refutation problem, does not extend here. And these guys came up with a clever way to make that work by doing some sort of thing where they showed that if 1 degree is too large, or if like canceling pairs doesn't work, then we might be able to cancel triples or something. It's not just like a naive thresholding argument. They have a sequence of thresholds where they sort of are all varying simultaneously in a clever way. It turns out the reason that this works and the reason that our thing works are both actually the same underlying reason. And I think we have just a slightly cleaner way of doing it, which is why we don't lose as many polylog factors. But more or less, the two proofs are exploiting the same key fact in the technical analysis, just in different ways. Okay, so yeah, that's what I want to say about locally decodable codes. The proof will be the even Q proof. And let's now talk about locally correctable codes. Okay, so what's the story for locally correctable codes? Well, again, we have read-mode codes, and we want to know if we can do better. Again, we can try Q equals 2. Hadamard code is again locally correctable. We again have the same lower bound because remember, locally correctable implies locally decodable. So if you prove a lower bound for a locally decodable code, you get the lower bound for locally correctable codes as well. Okay, so Q equals 2 is again the same. We can go to Q equals 3. We have the same construction. We again have matching vector codes. And you can ask, are these codes locally correctable? I said they were locally decodable. I did not say they were locally correctable. You might now believe that they're not locally correctable based on what I've said, but the actual answer is we don't know. And this may feel a little weird because this is an explicit construction of a code. Okay, I can like tell you explicitly what the encoding map is and so on. And so you'd think that if it's not locally correctable, you should be able to come up with a way to prove that it's not locally correctable without much difficulty. And if it is locally correctable, it usually should be pretty obvious from this construction, like you saw for Reed-Muller codes, why it actually is locally correctable. And here, we don't know the answer. And this was in fact an explicit question posed by Sergei Akanin in his survey on locally decodable codes, where he was wondering, is this locally correctable? And people have looked at it and they don't actually know the answer. Moreover, our best lower bounds here are actually just the same. So how do we prove a lower bound for an LCC? The paradigm is you give up and you say it's just a locally decodable code and you prove a lower bound for the locally decodable. The lower bounds are just coming from LDCs. And again, we have the same barrier at k squared, same as before.
I have a question.
Yeah.
So throughout these LCC and LDC, you're considering the corruption to be on the order of the block lengths.
Yeah.
If actually you have smaller corruption, are there lower bounds on like, what is the block length in that case for fixed queries?
Yeah, so the lower bound depends on the parameter delta and some very small polynomial, usually like 1 over delta squared or something. So,
Okay.
so if delta is something like 1 over polylog, then all these lower bounds are just being changed by some polylog factor. Now, if delta is like 1 over root n, that's huge and things get very different. So it depends what exactly you want to pick about delta, but usually delta is something like 1 over polylog, even when you take it subconstant, and then the lower bounds are basically all the same.
I
You're just
see,
adjusting them by like polylog k factors.
I see. So 1 over polylog means like 1 over polylog fraction is corrupted.
Yeah, exactly.
Okay.
Yeah, basically the dependence in all the lower bounds on delta is some polynomial on delta, small, even like a small polynomial. So as long as delta is not like, crazy, like 1 over n or something.
Well, I mean, sometimes in real applications, they consider a constant number of errors. Or
Yeah. No, that's a very
that's
different
a very
setting from
different regime, and then the
yeah.
lower bounds completely.
completely do not apply, yes. Yeah, you can, I think those are called like disjoint repair group or something.
Yeah, I don't.
There's
remember
some
the-
actual coding definition and you can study those. I mean,
Yeah,
they're much, I mean, the property is not nearly as strong as being locally decodable, so the lower bounds are not nearly as strong. Yeah. Okay, so that's the LCC story. It looks, as you might notice, basically the same as LDCs. The only difference is we actually don't even have a construction for Q equals 3. And so at this point, I asked this question, can we do better than read Molar codes? And the answer was yes for LDCs, but for LCCs, we don't know. And this isn't great. I mean, it's been about 30 or so years since we've really come up with this problem and studying it. And at this point, we have no better constructions than the simple construction of read Molar codes that I showed you. And at this point, if we've been trying pretty hard to get better constructions and been unable to do so, maybe we could just say that, maybe we can make the following conjecture. We can't get better constructions because they don't exist. That is, read Molar codes were actually optimal. Somehow this very simple thing that we did that was very easy to come up with is actually just the best thing that you can do.
maybe it's also important to say about the difference between LDC and LCC. In an LCC, for every bit of the encoding, you expect to have this hypergraph. So
Yeah.
there's something smooth about all the coordinates are the same. In an LDC, you only have these k special coordinates that you want to decode, so it's unbalanced.
Exactly, you only get k matching instead of n of them. And n is much larger than k, so that's like a pretty big, or pretty strong, feels like a stronger condition. Okay, so you can conjecture this. And again, I mean, we actually know this is true for Q equals 2, Hadamard code. And it's actually hard to prove for larger Q because, well, this work of Barkola, Shai, and Weingram proved that it's basically some stronger form of the Hamada conjecture from design theory. So this conjecture, design theory, when rephrased in the language of locally correctable codes, just says that read Molar codes are optimal design LCCs, where if you know what a block design is, this formally means that the parity check matrix of the code is a block design. If you don't know what a block design is, this should just think of it as like an LCC with extra nice structure. Okay.
Like every point occurs in the same number of.
Every
hyper-
pair occurs in the same number of hyper edges and the matchings are perfect. Yeah. In fact, the number of hyper edges each pair appears in is 1.
The hyper edges have size 3.
4 now. Think of them as size 4, where you like take C and then add U, where U is the label.
Okay.
Yeah. So then in that setting, each pair appears in exactly 1 hyper edge. And so then the H sub U's are perfect matchings of size like n minus 1 over 3.
Okay.
So that's the extra nice structure. Okay, so what we know for 3 LCCs is we have this absolutely massive gap between upper and lower bounds. And in the middle, actually, remember how I said the way we're proving lower bounds for LCCs is by giving up and proving lower bounds for LDCs. And so that approach has a provable barrier in the middle here where we have the construction for LDCs. So you're not going to be able to prove this conjecture or get anywhere close to it because of this barrier. We also have this technical barrier at k², though, as I mentioned, we already can go beyond it a little bit for locally decodable codes. So that was the story in 2022. Now, of course, we're in 2025. So let me tell you our results. And our main result is we prove an exponential lower bound for LCCs. We do this formally at first only for linear codes. Now, the way I've defined these codes is actually as linear codes, but you could define a version of the code where the encoding map is nonlinear, and then our lower bound would not apply. But all the codes I've shown you so far have been linear, so let's just roll with it and see what happens. So lower bound is 2 to the k to the 1/8, which is up here. It's beyond this LDC barrier. In particular, we're separating 3 LDCs and 3 LCCs because we're proving that there is a 3 LDC that is got a block length that's shorter than the best possible LCC. In fact, it's shorter by quite a bit. The second thing is this proves that those matching vector codes are not locally correct. Remember, I said that was something that we kind of believed, but we were unable to prove. And here we've proven it now via this roundabout way by showing a lower bound that goes beyond its length. The final thing I want to point out is that this is really the first time, at least for binary alphabet, where we're proving a lower bound for LCCs that is not just giving up on the LCC property and going to LDCs. And this is necessary if we want to go beyond this barrier, right? You can't go beyond this barrier if you're proving lower bounds for LDCs. So we did something non-trivial for the LCC. Okay, so that was our first result. There were then several follow-up works that kept optimizing the bound. The first was this work of Tal Yankovitz, where by just looking at our proof and optimizing it in a very, very clever way, he managed to simplify it and get some of the log factors away, which gets the exponent up to 2 to the k to the 1/4. And then there was a follow-up work of Omar and Venkat that gets us all the way up to 2 to the root k over log k, which you should notice is now 1 over root log k away from potentially proving that Reed-Muller codes are optimal. And they did it with a slightly different approach. They used this connection to rainbow cycles or rainbow even covers. And then they applied this rainbow cycle bound, this very, very nice work of Alon Bucic, Zarman, Zakharov, and Zamir on the rainbow cycle problem that's near type bounds for the rainbow cycle problem for graphs. And then they used that for their proof. So that was like kind of the key ingredient in their proof. And in our work, we proved a bound for design LCCs that is almost optimal. That is, it's 2 to the root k. This is an explicit constant in the exponent. I did not hide the constant there, which means that it's tight up to this factor of 2. That's why, by the way, I showed you the example of Reed-Muller codes and gave you the explicit constant. So you can see the exact constant. We almost have it. And in fact, this proves this Hamada's conjecture for 4 designs up again to this factor of 2. So if we got the tight constant factor, we would give the full proof of the conjecture, but we're just slightly off. Okay, so these lower bounds are for linear codes or the more special case of designs. Now, as I've been telling you in the talk, everything's been over the field F2, but you could ask for what can we show for other fields? And the answer is we can basically make these proofs work for small fields, but then this proof of Omar and Venkat requires characteristic 2, and so does our proof for the design case. Okay, so we can get exponential lower bounds over any small field, and once you want you got the really, really tight bounds, we need characteristic 2. But again, these lower bounds are only for linear codes. You can again ask what happens for nonlinear codes, and the answer is we can there prove some slightly better lower bounds. We get some lower bound that looks like k to the 1 over 2 epsilon, and epsilon here, well, I have to tell you what it is. It's the probability that the decoder works when I give you an uncorrupted code. Now, for linear codes, this is 1. Okay, but for nonlinear codes, this may be less than 1. But you really think of epsilon as being a small constant.
Wait, I don't understand. So for linear, epsilon is 0.
Epsilon is 0.
What's my lower bound?
Just 1 second, just 1 second. Okay, so this is slightly better than k cubed. That depends on what epsilon is, but if epsilon is rather small, which it probably should be, then you can make this much, much better, but just by a polynomial factor. And as Arit is pointing out, it makes sense to take epsilon to 0. And when I take epsilon to 0, no, it does not go to infinity. It goes to 2 to the k to the 1/5. Okay.
So you mean you have a lower bound for nonlinear 3 query LCCs,
Yes.
which is exponential.
If it has perfect completeness when the decoder is smooth. That's the technical condition.
Perfect completeness and a smooth decoder.
Smooth decoder.
Okay.
The problem is making a generic decoder smooth loses a little bit in the
Perfect
completeness.
completeness is not such a problem. It's more about
smoothness,
Smoothness means the distribution of the queries is kind of uniform.
kind of exactly. So depends who you talk to, like the cryptographers strongly prefer the smooth decoder definition because that's like the security definition, private information retrieval. So there's this weird thing where the standard definition of an LCC couples the definitions of delta and epsilon, like the error and the decoding success, in a way that's kind of annoying because you'd like to say that if I have fewer than delta errors, my decoding success is larger than 1 minus epsilon. But formally, the only thing you can say is that like, if I'm below some cutoff threshold of errors, my decoding success is above some threshold, but you don't get some trade-off as like a function. If we got some nice trade-off as a function, like if I tell you the error threshold and you tell me some function of delta is success, then again, I can get the same thing without assuming smoothness. It's just really, the way the lower bound works is that
You can alter your definition
yeah.
so that what's the alteration that you?
So let's say if I give you, if there's delta errors, you succeed in decoding with probability 1 minus 100 delta. So there I have some
So there is
smooth,
some soundness function, S of delta.
yes, of delta, exactly.
And your success is 1 minus S of delta. And if, so okay, so you have such an S, then what is your result?
Then we can get, it wouldn't be 1/5, but it would be some other 2 to the k to the some other. Yeah, I mean, basically the way it works is that the delta parameter doesn't matter so much. We could take that to be 1 over polylog, we're only changing the constant of the exponent, but the epsilon parameter matters a huge amount. So there you could just, if you have this connection, you can make delta be small, like subconstant, but then epsilon, we only need to be like smaller than 1 over some polylog.
Will we see it?
No, we will not see it.
Okay.
Please don't. Please don't make me do this. No, so what we will actually see today is some very, if we get time for it, we'll see some very basic intuition behind the proof.
Okay, and Peter, is that like proof you were saying, is that like a reduction to the linear case? Is how you get that or no?
No.
Okay,
No, there's actually, so the standard way of connecting the semantic and combinatorial definitions is by doing some generic reduction. The thing, and the reason why we didn't get a lower bound for nonlinear codes in our first paper is that this reduction does not work. When we see the intuition behind the proof, the reduction will not work for the way we are going about proving these lower bounds. So what we instead had to do is sort of open up what the decoder actually does and not do the reduction, but like do it within the proof. And this wasn't actually that complicated to explain, but it's kind of a pain to write out.
Maybe we can ask you over lunch.
Yeah, you can ask me over lunch. And actually, the first version of this paper, we even only got to k to the log k on the epsilon equals 0 case, and then I realized I did something a little bit silly, and there was a way to make it exponential.
By the way, the nonlinear, the alphabet can grow a little bit or?
Yeah, same sort of thing with it. Well, locally correctable codes are a little bit weird when they're not over binary alphabet for nonlinear codes. Because you're sort of saying like I read symbols that are these big symbols of these 3 locations, and then I want to recover like another big symbol.
You're right.
So it's
okay,
kind of
I
weird.
see.
Yeah, I guess
Uh-huh.
you could probably make it work if you really wanted to. I don't think we did though.
Having different kinds of symbols throughout the code word is kind of weird.
It's kind of weird. Exactly.
Okay.
Okay, so that's the whole sequence of results. The main thing is our lower bounds now look very good. Before they were k-squared, now they look really good. And so, yeah, so that's what I want to say about locally correctable codes. I'm just going to briefly, before we go to the break, say a few words about the proof overview. So the proof overview is going to follow the same strategy that I had on the first slide of the talk. So we know what this reduction is from the QLDC to the family of sparse linear equations because I defined my LDC to be given by a family of sparse linear equations. Okay, so it's an LDC if this system of equations is satisfiable for all B. Semantically, this is encoding the fact that our decoder should actually work with probability 1 when I give you a code. Now, the way we're going to prove a lower bound is by showing there exists some B such that it's not satisfiable. By showing that if I pick a random B, then say with high probability, psi of B is unsatisfiable. Semantically, this means there is some message such that regardless of what encoding I pick for that message, the decoder does not work. So the decoder doesn't work. So there's no code. It's not locally decoded. So that proves the lower bound. Now, unlike the case of refutation that I discussed last week, where in refutation, remember, the main goal was really to certify unsatisfiability using an algorithm that was running in some bounded amount of time. Here, there is no algorithm. I do not care about running time at all. All I care about is showing unsatisfied, which means that these existential tools like probabilistic methods, so like Chernoff plus union bound, are at my disposal. They were not at my disposal last week. And last week, the instances that I gave you are very easy to show that they're unsatisfiable using probabilistic method. So you might think, okay, this should be easy. I just use probabilistic method and go home. Well, the problem is it doesn't work. Kind of dumb. Okay, and the reason it doesn't work is that the number of random bits I have here is very small. I only have k random bits, which is the length of the message. The number of variables is the length of the encoding. That's always larger than k. In fact, for the 3 LCC lower bound that we're going to prove, k is going to be polylog n. For the design case, it's even log squared n, or like literally log base 2 squared of n. So it's even up to a precise constant. So k is very, very small, which means you don't have enough randomness to do these union bound types of arguments. And the punchline here is we're still going to be able to make it work using the spectral approach. Okay. And for LCCs, there's something a little bit tricky that's going to go on where we start off with a system of homogeneous linear equations, and this approach kind of wants us to have this random b, so we're going to convert it to some instance which has these random b's on the right-hand sides, and we're going to do this also by just starting with the original system of equations and deriving new equations from those system of equations, and then we'll refute the derived instance instead. There's something a little bit more complicated going on in the LCC case, but more or less the picture is the same. Okay, so that's the strategy. That's the proof overview. And now it's time for our break. Okay. Are we good?
Yeah.
Okay, so let's come back. Okay, yeah, so what we're going to do now is we're going to prove theorem 1, which is the LDC lower bound for even q. In fact, the theorem is true for both even and odd q. And the theorem just says that if I take q uniform matchings h1 through hk of size delta n, such that the system of equations that I had on my slides is satisfiable for all b, then k is at most n to the 1 minus 2 over q times log n. In fact, our theorem statement for the odd query case is like literally the same log factor everything. Okay. So I've rearranged the k to the q over q minus 2 as an n to the 1 minus 2 over q, because this is what the way the proof will come out, and you could, of course, just rearrange to get k to the q over q minus 2. This is q minus 2 divided by q. Okay. So that's the first theorem we'll show. The second theorem, the LCC statement that we proved, is that if we have 3 uniform matchings h1 through hn, such that I define the system of linear equations, then the dimension of the solution space of these linear equations is bounded above by polylog. Okay, we will not prove this. It will take too long, but we'll first do this and then we'll give some intuition for this proof. Okay, now you may have noticed that instead of writing sums, I'm writing products here. And that's because, like last week, I'm going to be switching now to plus minus 1 notation. So my linear equations all become products. I'm mapping 0 to 1 and 1 to minus 1, just the kind of standard embedding of F2 into the reals. All right. So again, let me just start by summarizing the main steps we had in the proof for last week. Okay, the first thing we're going to do is I'm going to define this polynomial psi b of x. Now this polynomial is just sort of the same thing as last week. We're going to sum over all the constraints. So sum over I equals 1 to k, sum over c and h sub I. These are the constraints. And then I put the product of v and c, xv times b sub I. Okay. Now in plus minus 1 notation, if I plug in an assignment x, this thing is plus 1 if the constraint is satisfied, minus 1 if it's unsatisfied. So this thing is counting the number of constraints satisfied minus the number that are violated. Okay.
Sorry, Peter, can I ask?
Yeah.
Are you planning on talking about the locally correctable codes
Yeah.
or like the
I'll say the
exponential-
intuition behind the proof. I just won't give you the full proof.
like for one of the results that gets some exponential power?
Yeah,
Okay, sounds good.
I'll show you that there's one main idea behind all the proofs,
Okay,
which is the same main idea that appeared in our first work. Sure. So, and then everything else is like figuring out what to do with that idea. In fact, pretty much all but Omar and Venkat's paper are doing essentially the same thing with that idea, and Omar and Mecca's papers.
You're saying that idea is different than what you're talking about right now?
What I'm talking about right now, I'm gonna talk about locally decodable codes.
Yeah, okay, sounds fine.
So we'll first do locally decodable codes and then we'll see, yeah, some more stuff. Okay, so this is just set from last time. I mean, I define my polynomial, I define the value of my polynomial should be the maximum over x plus minus 1 to the n of psi b of x, same as before. And because this is satisfiable, this is simply delta n k, because I have delta n k constraints, and there exists an x that will satisfy all of them. So that's the value. Okay. The other thing we need to do is we need to recall these Cayley graphs over 0, 1 to the n, which I'm going to identify with 2 to the n, so subsets of n. You can think of a subset as being identified by its indicator vector here. All right. So I'm going to define the adjacency matrix M to be, or the matrix M to be the adjacency matrix of the Cayley graph with group 0, 1 to the n, so F2 to the n. The generators are H1 through HK. And last time, remember, I put signs on the edges. Again, I'm going to put signs on the edges here, and the signs are going to be B1 through BK. So that is to say that all hyper edges in H sub I get sign B sub I. Again, this is mimicking, what's going on here. And we can write the matrix M by just saying that M has ST entry that looks as follows. It's B sub I or 0, and it's B sub I if the symmetric difference of S and T, or their addition mod 2, is in the hypergraph H sub I, and it's 0 otherwise. And like we did last week, we can write this matrix as some nice form. It's just the sum over I equals 1 to the k, sum over the matchings, some coefficient B sub I times the sum over the hyper edges, some matrix M sub C, where M sub C is just the Cayley graph with only using C. Okay, so this is just splitting up my edges by saying the number of the edges I have are the ones where I sum over my hypergraphs and sum over the edges in the hypergraph, and I put an edge for that generator with sign B sub I. Notice, we're mimicking the structure of psi b of x here. So the other thing you must remember are the induced subgraphs. So here I'm going to let V sub L be the set of S, size S is equal to L. By the way, at any point, if you guys are not remembering the stuff from last week, let me know and I can explain in more detail. I'm just going through this a little bit quickly because I did cover this in detail last week, right?
Please write bigger.
Please write bigger. No. Okay, I'll try. I'm sorry, Abby. Okay. So I'm going to take the induced subgraph on this set of vertices of size L. So my matrix A,
It's not only Avi, it's the thousands that will watch the video.
thousands that will, yeah.
Okay.
So, sorry, M restricted to B
That's good.
is equal to. Okay. So I'm defining my Kikuchi graph or induced subgraph as just this Cayley graph or signed Cayley graph restricted to this vertex set. Okay. I can again write A is equal to the sum B sub I times some matrix A sub I, where A sub I is the sum C in H sub I, A sub C. Now, I do want to point out the Cayley graph using only one generator is a matching. In fact, it's a perfect matching. So A sub I or A sub C is the induced subgraph of M sub C on these vertices. So A sub C is some matching, but it might not be a perfect one. And in fact, you should notice we're again taking a induced subgraph on size of VL is capital N, which is N choose L. Okay, so we have very few vertices relative to the 2 to the N vertices that we had in the original Cayley graph. So this is an induced subgraph on a very small number of vertices. And of course, if you take an induced subgraph on a small number of vertices, you may have lost all your edges, right? So the key claim that we showed last week is this process does not delete all your edges. That is, this matrix A sub C has capital D equals Q choose Q over 2, N minus Q choose L minus Q over 2. I guess non-zero entries in the matrix, which is the number of edges times 2.
This is Q, choose Q over 2 to choose which ones are in your
S,
first and
yeah.
then second
And
one.
then this is the other part of S that cancels with the other part of T. Yeah, if you remember from last week, we had a set S and T whose symmetric difference was equal to C if and only if they looked like the following. S had half of C. C had what I'm going to call C other half. And then there was some set Q, and then this was what these sets look like. So when I
So the
take,
first part is to choose the way to split to halves, and the second part is to choose capital. Q.
exactly. And the important fact is that capital N divided, or capital D divided by capital N, the number of vertices, is about L over N to the Q over 2. Now here you can observe that it's very important that Q is even, because I can't split C in half if it has odd size. It's just how it works, right? That's what an even number does. Okay. So the other key claim is that we can relate value of psi b to the spectral norms of these matrices. So what we showed last time was value of psi b is equal to the spectral norm of the matrix M. And also that it's at most N over capital D, the spectral norm of the matrix A. If you remember the proof, it's because this isn't a Cayley graph over an abelian group. So we have an explicit characterization of its eigenvectors, and the eigenvectors correspond to assignments X, where the eigenvalue is just psi b of X. So then the maximum is the maximum. And here what you do is you take those eigenvectors and you project them down to this space of V sub L vertices, and the quadratic form is roughly preserved. You just get this capital D factor because that's how many edges you have. And then capital N is the L2 squared norm. So that gives us this inequality. Okay, so these were kind of the key facts from last time. And then this leads us to the final part, where what we would like to do is now bound the operator norm of this matrix A. Now what I'm going to do is I'm not going to bound the operator norm itself. What I'm going to do is I'm going to bound the expectation of the operator norm over the choice of B. Okay. And my claim is that this is going to be at most delta N capital D over capital N times root K L log. All right, so let's first see why this claim will win. Actually, there's one more condition. This only holds if L is at least n to the 1 minus 2 over q. So there's some lower bound on L which will make this condition true. Okay, so let's see why this implies the theorem. So the answer is pretty straightforward. I just have to follow all the inequalities that I've done so far.
So interesting. So now I'm confused already by the approach, because last time I was happy that you had this Cayley graph. It gives you the perfect answer, the maximum, the spectral norm is the value. And then you were looking for an algorithm, so you couldn't afford it, you had to take some approximation to it. Now you said, oh, now I don't need an algorithm, I'm happy.
Yeah.
But still you want this approximation because it appears in your bound, so
So what's going on?
yes.
The answer is, this is probably why we are not getting tight lower bounds. We don't know how to analyze the bigger matrices.
I mean, but you know what the,
We know
What would you
whatever it
like to
does will give you the
analyze?
right answer, but I don't know how to tell you that the right answer is something. Right? Like, so what you've said is that if I compute the operator norm of M, I will determine whether the instance is satisfiable. So the only thing I need to do is compute the expectation over B of this operator norm.
Okay,
Now I need to bound that by something. I don't know how to do that.
oh,
And if I could, I would get the optimal bound. So this is a real deficiency in the proof that we cannot take, as you will see, actually taking L larger is going to make our bound, actually, we'll see this in like, once I finish writing this out. You'll see that taking L larger is going to make the bound worse.
so a priori, you could have expected that the larger L is, the better your bound.
In fact, the larger L is, the bound should be better. If I mean, if I change this
more
to a less than or
information.
equal, then the bound can only get better as I increase L. But somehow my proof cannot show this. And so,
I have some like very vague intuition for why it makes sense to do this, I think. I could try to share.
it doesn't make sense.
No, like, so there's some things in additive combinatorics where it's like you start with some set A and it's in some ambient space of unbounded size, and the only thing you know about A is like some local fact, like that it has small doubling.
Yeah.
And then sometimes you can take this and like convert this to the situation where actually I just want to think of A as being embedded in some small subgroup or something. And so it's like now dense inside the more ambient space.
The
And-
smaller ambient
And you throw, now at this point, you throw away the information like that it has small doubling. Now you just know that it's dense inside this like closed space. So I think this idea of like
You are sort of embedding it in a space of dimension like n choose L instead of a space of dimension 2 to the n,
yeah,
which is
I think that
perhaps helpful, but
analogy, yeah.
If you dense, don't you automatically still have a small doubling? Usually you don't lose too much.
Exactly, I know, I'm saying, and just like mechanically, you get to work with this new assumption that's equivalent and just better, like I agree.
So you're saying really, if your intuition is true, this embedding is what you have gained?
yeah, I mean,
I mean, in additive combinatorics, that makes sense. You use the small doubling to embed your set in some place with structure, a subspace.
So like a
In a
Hamming ball
dense way.
has some kind of
So
structure.
that's already giving some structure to your thing. Here, what is getting my, what?
Like
It's
a
like a
Hamming
ball.
ball has some sort of structure, right? That's the analogy. It's like not quite closed, you know, it's like somewhat, sorry, even just additive structure. It has some additive structure, like it's not closed under addition, but like the sum set of a Hamming ball with itself is like another Hamming ball with bounded size, that kind of thing.
Yeah, but maybe to Peter's point, maybe here we're losing because actually for small Hamming balls, the doubling is fairly big compared to the size of the ball. So maybe quantitatively.
But still a lot smaller than like an average or like an
A
arbitrary
random
set.
set?
Yeah.
Even for a small Hamming ball? And you think that's relevant here for I mean, here, we're talking about approximating spectral norms, so.
no, I think the answer here is that, I mean, if I just slightly change the definition of the matrix, I can prove that the larger spectral norm bounds are only giving me better bounds. Can only potentially give me better bounds, right? But then the other thing I can show is that, well, the only way I can prove that this matrix gives a good bound is by first bounding this one and then doing that. So there's some, I think the real difficulty is actually in analyzing the larger matrices. As you'll see, the analysis, the way I'm going to analyze this matrix is actually going to be not so complicated.
So you expect if L gets larger, you shouldn't get a bigger bound
You should-
on the,
Yeah, the bound on
even
this,
though here it is.
well, I mean, formally, right, this
Oh.
spectral norm is at most of this, which is equal to this.
Mhm.
So clearly, if I could use this to prove a lower bound, then this is also proving the lower bound. But the way I can prove that this is proving the lower bound is by first passing to this matrix.
If you want to point to something specific that could be helping you about this, it's like just that at some point we might want to do the trace method, and then just for the trace method, it's like more efficient if the matrix is not as big, right? Like that's
No,
exactly.
but yeah, so
right.
that's correct.
Uh-huh.
But
Why?
one thing, here's maybe a way to explain why
Okay.
this is a bad idea, actually. Which is that if I pick the matchings H1 through HK at random, this approach will not give me the right bound. It actually gets stuck at the bound that I'm proving. Okay, and the reason for that is when you do the trace method, the length of these even covers that you find are short. And I can show that these hypergraphs, actually, if I pick even random ones, that's will give me the extremal. It's sort of like saying the rainbow even cover bound is the one I'm proving. But I care about odd colored even covers, which could have very long length. And for that problem, I don't think this is tight.
Why is the trace method more efficient for smaller graphs?
When you take the trace power, you only need to count cycles of length log size of the matrix or size of the number of vertices. Because there's some factor of number of vertices out front that you need to remove when you take 1 over rth powers, where r is the length of the walk.
Right.
So you want to take r to be about log n, maybe like 2 or 3 log n or something. And that's actually where this L log n term.
It's like log of n choose L.
Yeah, this is log of capital. Okay, so let me finish this proof. Okay, it's pretty straightforward. I just have to chase all the inequalities across the board. So I had delta nk, most expectation. Well, I didn't actually need the expectation here. It was at most. It was always a lower bound on value of psi b, but I can take expectations, it's still a lower bound. And this is at most n over capital D, expectation of the spectral norm of A. Now let me just finish this. So this I have is bounded by this, and delta n capital D over capital N. As you can see, the capital D and capital N are going to cancel with each other. I have a delta N, it's going to cancel with this delta N. So this implies K is at most. Oh yeah, there's a constant factor out here. There's a big O. I've been hiding my big O. Okay, this implies that K is at most root K L log N, or in other words, K is at most L log N. Okay, so that's the bound I'm proving on K. Now, as you can see, I want to make L small to make my bound better. And the thing I'm gonna get stuck at is n to the 1 minus 2 over q, because I need L to be at least this amount so that I can bound my spectral norm. So I do that, I plug in n to the 1 minus 2 over q, and I'm done. So here you can see from the bound why it helps to take smaller L, but intuitively, I think the real reason why this is bad for larger L is because our spectral norm bound when L becomes large is actually bad. This informal argument I gave you about these rainbow even covers is at some level saying that the spectral norm bound is actually tight for the value of L is n to the 1 minus 2 over q. But then as L becomes larger, it's not. Okay. So let me. Let's get rid of the theorems. So I need to now prove my spectral norm bound. Okay, so that's the last thing I need to do to finish the proof. Okay, so here's the proof of the plane. I'm going to let A, as I wrote it before, be the sum of B sub I, A sub I. Remember, B sub i's are plus minus 1 independent random variables. So this is a sum of mean 0 independent random matrices. I can apply my favorite matrix concentration bound, matrix Kinshin. And this says that the expectation of the spectral norm of A is at most square root of sigma squared log capital N, which remember this term was the L log N term. Okay, so I just need to tell you what sigma squared is, and sigma squared is the variance term, which is the spectral norm of the expectation of A squared. Okay, now I can expand this out. When I square A, I get the sum of BI times BJ times AI times AJ. Now these are independent, so when I take expectations, and mean 0 by the way, so when I take expectations, all the terms that have BI, BJ for I not equal to j just drop out, they're 0. And I'm left with the diagonal terms where I sum just BI squared, AI squared. BI squared is 1 because it's plus minus 1, So this is sum I equals 1 to k, ai squared. Okay. I can now apply triangle inequality and bring the norm inside. And I would get a square up here, but because this is ai squared, I can also bring the square out here. Okay? So in order to finish the proof, I need this to be, well, the sigma squared, if I just match terms with the claim way over there, I want this to be at most delta n capital D over capital N squared times k. Okay? Or maybe I'm allowed to afford a constant factor loss, it's not a big deal. Right? So what I really want to show is that the spectral norm of each a sub I is at most delta n capital D over capital N, maybe times some constant factor. Okay. Now here's a simple fact. The spectral norm of this matrix, well, it's a graph, it's the adjacency matrix of a graph, it doesn't even have any signs in it. This is at most the maximum degree. Okay, well, we do know that the maximum degree of a graph is always at least what? Well, the average degree. Okay, again, duh. I'm not doing anything too complicated here. And let's compute the average degree of a sub. I have delta n, delta little n hyperedges. Each hyperedge contributes some capital D number of hyperedges, or number of edges, or I guess D over 2 edges, so capital D to the average degree. And I have capital N vertices. So the average degree is equal to this delta little n capital D divided by big N. That's exactly the bound that I want on my spectral norm, by the way. So what I really want to show is that the maximum degree of a sub I is at most some constant times the average. That will be what I want. And this you should think of as some approximate regularity condition. All right. So I want to show that these graphs are approximately regular. So now I can go and I can compute the maximum degree. All right, let's compute the maximum degree and see what we get. So I'm going to claim, well, we know that a set S has an edge for set C, for the hyperedge C, if and only if S intersects C has size Q over 2. That was the condition. We saw that right here. Okay. So the way to make the degree of a set large is to pack in these half hyperedges. Now we're working in a matching, so the hyperedges are disjoint. So the optimal way to do this is to have S to be like C1 through CR, where this is really half of each of the hyperedges. So here R times Q over 2 is the size of S, which is L, or in other words, R is 2L over Q. And the degree of S is R, because for each of these hyperedges, I can swap the other half in and get another set T. Okay? So the maximum degree is just 2L over Q. In fact, this is the maximal example. Now we can compare 2L over Q versus this delta N capital D over capital N. And this guy, I know just by my estimate here, that this is about L over N to the Q over 2 times N. If you rearrange this, you will observe that this is always larger. And so we're in trouble. The maximum degree is much larger than the average degree. And in fact, if you were to plug this into your spectral norm bound, you will not get anything at all. You'll get the bound of k is at most n log n, which is trivial. So this is a problem. This graph is not approximately right. And I want to point out that this whole proof I have been doing for this problem, but I haven't actually made an assumption on the hypergraphs yet. So remember, we assumed the hypergraphs were matchings
Didn't you just assume it
to show what the maximum degree is, but like, that's bad for me. Okay, I'm showing the maximum degree is large. I mean, if the hypergraph is not a matching, this will be even larger.
Right.
So life will be even worse. Okay, so when I'm trying to bound the spectral norm, so far I have not used the fact that it's a matching, other than to show that, well, in the matching, the degree is large, but it turns out the degree is large for it's even worse for non-matchings.
In other words, you use the matching to show the degree is not that large.
But it's still too large to
It's
make it
still
work.
too
It's still too large. I think the point is, and even in the good case of matchings, the degree is still too large.
Right.
Okay, but the point is, haven't really used the matching property yet in the proof. All the steps I've been doing so far have been generic for any hypergraph. Okay, now the theorem is pretty clearly false if I don't use that H sub i's are matchings. So if they're arbitrary hypergraphs, the theorem's false. So I need to use the fact that they are matchings. Okay, so the key observation that will rescue this whole proof is that the set S here is rather atypical. This is not what a typical vertex will look like. Okay, and the key observation is because H sub I is a matching, if I pick a random vertex S, degree will be about some constant times the average. Okay. So that is, most sets have the right degree. It's just there are some weird ones in there. Okay, let's prove this, or maybe proof sketch. I'm not going to give you a full formal proof, but this is not too difficult to show. So instead of picking a random S by picking a random set of size L, I instead am going to sample S from a binomial distribution where each element is included with probability L over N. This will just make, for intuition, make things look a little bit easier. Now remember, S gets an edge for C, that is its degree goes up by 1 when its intersection with C has size Q over 2. So the event, the probability that S intersects C as size Q over 2 is going to be about this probability to the Q over 2, because if you think about it, I need to get like Q over 2 hits where I have a Q of them. And so maybe up to some constant factors in Q, this is going to be L over N to the Q over 2. The other thing I can observe is that the size of S intersects C and the size of S intersects C prime when C and C prime are disjoint, these are independent. Because we're drawing from a binomial distribution, so this depends on some subset of these flips. This depends on a different subset, so they're independent. So what this means is that the degree of S is distributed as some binomial where the number of hits I can get is delta, or the number of samples I'm drawing is delta N, the number of hyper edges, and the probability of getting like a 1 is about L over N to the Q over 2. Okay, I can use concentration to now show this is concentrated around delta N times L over N to the Q over 2, which is my average degree. Okay. So a bit more formally, what we were able to show is the following. With a bit more effort, we can show that there exists a subgraph B sub I contained within A sub I with two nice properties. The first is that I'm taking a subgraph. I want to take a non-trivial subgraph. In particular, I want a subgraph that has a lot of the edges, or most of the edges. So that is to say that the average degree of B sub I is at least, say, half times the average degree of A sub I. Okay, so we've kept most of the edges, or half of the edges. The other condition is that B sub I satisfies the condition that I want. That is, its average degree is at most, or sorry, its maximum degree is at most some constant times the average. Okay, so what we've done here is we said, okay, A sub I as a graph itself had some weird vertices in it, but I just removed those. And what I'm left with is something that satisfied the conditions that I actually want. And we can do this because H sub I is a matching. H sub I is arbitrary, you might not be able to do this. Okay. So that's it. We don't use A sub I actually in the proof, we use B sub I. In fact, you can show something slightly stronger than one, which is that you can show for all C in H sub I, B sub I has exactly maybe D over 2 edges from C. So that is for each hyper edge, we've kept half of its edges. So this finishes the proof. I just switched to B sub I. This condition here or this condition here is enough to say that the spectral norm of the matrix, or the B matrix, still bounds the value of the instance. Because this is saying kind of for every monomial, I pick up a D over 2. I guess I erased it, but okay, here when I have the value of this being opposed to this, I now need to add a factor of 2. Okay, but like factor of 2 is no biggie. So that's totally fine.
Why do you add a factor of 2? Are you bounding the 2 norm of
this
A
is-
by B?
This is B,
By 2 times the 2 norm of B?
because B only has half the edges, so I've lost a factor. Yeah, that's it. There's a D over 2 is because there's a D over 2 there.
Mhm.
That's it. Okay, but I mean, I've already been ignoring constants, not a big deal. And this finishes the proof. So this claim here was actually, this was false. And to make the true claim, I need to make it with B. Okay. Now, there's one thing I kind of slid under the rug here, which is this little condition. Do you guys see where I used this?
Kitchen or
No, so the correct answer is I'm going to look at the average degree. What is my average degree? It's this guy here. Now, if my average degree is like much smaller than 1, the maximum degree is always 1, guys, like, because it's a graph. Edges come in like 0, 1, you know, like you can't get like half an edge. So the condition on L is such that exactly the maximum or the average degree is like at least 1. That's it. And I need that because otherwise this is clearly false. Cannot have this condition hold when I have average, or when my
That
average
shows
degree.
why L wants to be large, but why does it want to be small?
It wants to be small because the bound I actually get out of all this is K is at most L. So.
Yeah, but I'm looking for, okay,
No, it's because the spectral norm bounds are literally just like the degree times root K log size of the matrix. So if the size of the matrix goes up, you keep losing more and more in this log capital N term.
That's what you do at the end of the trace method, right? You bound the spectral norm trivially by the Frobenius you get.
Yeah. Exactly. I mean, there's a lot of interesting work in random matrix theory trying to investigate when this term is or is not necessary. But none of them really work in this setting, as far as I can, or as to the best of my knowledge. I don't know of any of those results that will tell me that I can remove this factor. So there are some results in random matrix theory. Like if I pick a random matrix plus minus 1 entries, its spectral norm is not root n log n, it's root n. So the log size of the matrix is gone. But here I have. This has to be there, by the way, for L equals this thing. It's for larger L that I don't think this is real. So maybe a good way of summarizing this is when I go all the way here, just erase this, don't need it anymore. The quick summary of the proof.
Oh, oops. I wrote bigger for 25 minutes ago.
Well, you can kind of see it on the video.
I'm sorry, okay.
I'm sorry.
I was so engaged with it.
So, okay, to summarize the proof, the bound we're proving is k is at most L log n. And L is such that the average degree of each a sub I is at least one. So I want to pick the smallest L, that'll make my average degree go up, or be at least one. Remember, the average degree is like L over n, the Q over 2, where Q is the size of the hyperedges times the number of hyperedges. Okay, so I would like to have more hyperedges and I would like to have smaller area. That would be the best for me. But you know, we're given the hypergraph we're given, and we're given the arity we're given, so there's not much wiggle room here. So I'm going to view this as a heuristic, okay? Which is to say that if I give you a system of constraints of some arity, I can predict a lower bound that's k is at most L log n, where I choose L to be so that this thing is at least one. Now, I'm going to say this is a heuristic even when Q is odd. So far, everything I've been doing is for Q equals even, and the whole difficulty in executing the proof for odd Q is to make this heuristic work for odd Q. But this heuristic again is predicting a bound of k is at most n to the 1 minus 2 over Q if I plug in an odd value of Q here. Okay. So that's what I want to say about theorem 1. We essentially gave a proof of it. I mean, I didn't fully do this subgraph step for you, but I sort of sketched why it's true. And other than that, every other step of the proof is really there. Okay. So now, the final minutes, let me talk briefly about the LCC case and what we do there that's different.
So can we just
Or-
stop for
or
a
you-
minute and just to summarize
Okay, sure.
what you did? You had the Cayley graph, you approximated it by this restriction to Saint-Giselle. And then you calculated the norm in that world. And you were hoping that this is a good approximation
Mhm.
for the norm for the entire matrix.
Yeah, and it turned out it was actually horrible with the initial definition of the matrices that I used. So then I had to do this modification, make them approximately regular.
No,
And then
it wasn't horrible. The bound, I mean, for the initial matrices AI, it could be that the spectral norm is also the same. It's just that.
No, the
bounding
spectral
by the
norm, I think
max
is, I think for
degree.
there, I can, if I stared at it long enough, I could prove the spectral norm's bad. Like this is not like,
Really? I mean, suppose you have a graph with few degrees of maximal degree, you would need the eigenfunction to concentrate there. Otherwise, okay, maybe,
Oh, yeah,
okay,
you can
you're
do
saying
it.
that's what.
no, I mean, this is the intuition, I mean, the step of finding this regular subgraph comes from the odd case of the refutation problem. Where for the refutation problem, remember, I only define these graphs for even Q, but for odd Q, you define a different graph, and your hope there would be that even in the case when the hypergraph was random, that the just spectral norm bound gives you a good refutation. Because remember, in the semi-random case, I had to do some reweighting last time.
Yeah.
But
Okay.
the point is that the spectral norm bound there is truly bad, even when for a random hypergraph. And like the same thing is happening here. For H sub I being a matching is kind of like it's random, and there the spectral norm bound is actually bad. Like, so the step of removing the high degree vertices
And
is,
now I'm lost again.
Okay.
I thought, okay, when we wrote that the inequality less than 2 times the norm of B.
Yeah.
Was there any sandwiching place where we wrote less than the norm of A?
no,
There
no,
was not.
there was not.
So how do we know this is less than the norm of B?
Good. So the point is that B has exactly D over 2 edges for each C. So I can do again the same calculation that I did that proved that A sub I spectral norm or A's spectral norm bounded the value of psi B. And the same calculation works when I just swap A with B.
Uh-huh.
Because the real only thing we used in the matrix A was that it has exactly D edges from each C. So the only thing that changes is D becomes D over 2.
Sorry, again, is it super important that it's exactly D edges, or could you have at least?
For linear, at least it's fine. For nonlinear, exactly is important. Yeah, the basic, okay, for nonlinear, the main thing that happens is this value is not delta nk, there's like an extra epsilon. And there, what I want is the quadratic form on the matrix B to exactly equal the polynomial psi. So then the exactly part is to say that each monomial appears the same number of times. Now, if it's at least d over two, what I can do is take the edges that have more than d over two and just start removing edges until it has exactly d over two.
Can you remind why, okay, can you remind the bound, why does the norm of B bound the norm of M? The initial
Yeah.
Cayley graph.
So what you
Why
do,
is that condition relevant?
so you look at some quadratic form with these Fourier characters, but on B.
Mhm.
And what this is it's the sum over C, where I then look at this quadratic form on B sub C. Okay,
Oh,
then
and
there's.
then kind of the vertex is irrelevant, it cancels out, only C remains.
Yeah, the only thing that, I mean, basically, this is a Fourier character, so chi x sub s times chi x sub t is chi sub x of the symmetric difference, which is only C here.
That's-
And then I pick up a d over two for each C because that's how many edges are there.
Okay,
So then I get this multiplicative factor of d over two, which is what's there.
okay, I see. This is important.
This is important, yeah.
I'm even confused about something more basic, like why do you even move from M to A? Now I'm confused, because I feel this L is pretty large, right?
Yeah, I mean, it's like n to the 1 minus 2 over q, I mean, if q is 3,
So what's the gain of switching to this slightly smaller? Like,
the gain is that I can actually compute the spectral norm. So
uh,
like my bound on the spectral norm of M right now, just with this approach, would be the same thing as here, but L is M.
Mm-hmm.
Right, and that loses everything. So there's some gain from what Xander said, where we're kind of embedding this thing into some matrix of dimension that's like much smaller than 2 to the n, and so that's giving us some small gain.
If L is N, you get an upper bound which is K less than N log N. That's trivial.
and what step is the problem occurring though? Is that applying the Kinchin inequality?
Yeah, so the Kinchin inequality loses the log size of the matrix. The size of the matrix is L log little n.
I see,
So
so
this term here, the loss down here is literally the Kinchin log factor.
So kind of in retrospect, you know that the upper bound on M is better than
Yes,
um.
yeah, but how do I prove it?
But you need to find.
How do I prove
Way to
it? It's hard.
but this is a Cayley graph, right? Wouldn't, I just, you know, all the eigenvectors and
Yeah,
stuff.
but how do you compute their eigenvalues?
Okay,
Like, I mean, you could write it down, yeah, you know it's psi v of x, what's psi v of x? I don't know what it is,
Okay.
like I'm trying to bound that.
I see.
Sort of, yeah, you see what I'm saying, like
You're trying to bound the value
of
of
psi b for,
psi b meaning, yeah.
yeah, so pick a random b and tell me what's the maximum over x of psi b of x. I don't know how to compute that, I mean, this is the best way we
So
have,
that's what you know.
so. You're right that this feels like there's things you could do that would be better, but I don't know how to make them work, it's not so easy.
I mean, you can use an STP, I don't know.
Yeah, but what does it give you? Right, I mean, yes, you could use an STP, I could, yeah, but like, what, like,
Okay.
how do you analyze it? I can give you things, I mean, this matrix M, as I told you, it's computing the right answer. But how do I prove that it's what it is computing, right? See what I'm saying? Like, how would you prove it's outputting something that's like n to the epsilon? I don't know.
Wait a minute, you know that it's computing the right answer?
We know that what, like, if my algorithm to determine the optimal threshold was like, give me the matchings, write the matrix M, computed spectral norm, if it's less than 1, output not an LDC. That will determine exactly when H1 through HK form an LDC, right? How do I prove that this is outputting not an LDC with probability 1 when H1 through HK has K larger than some threshold? Like, what is that threshold? That's what we need to determine.
We don't know the correct
But
threshold.
we don't know the correct threshold. But like, here we're saying, okay, when K is like at least n to the 1 minus 2 over q, then it's outputting not an LDC with probability. But what about smaller k? Right. We also know that there's some other threshold from the matching vector codes that if k is below that, then there is a construction, so that it won't work, but in between what's happening, we don't know.
Sorry, now you can say something about us.
Yeah.
That's okay, we
can take more
we can
time.
take more time.
Yeah.
It started late,
Started. Fine.
now you can write bigger.
I can,
Yes,
it's hard for me
yes.
to write bigger. I mean, I can only like write down to here on the
Write
page.
it, yeah.
So it's like, no, it would be easier to write bigger if the boards could slide up. It's just my spacings. Okay, so the point here is we have this heuristic, okay? We're saying the bound we're able to prove via this approach, which is, as we pointed out, it's not that complicated the way we're computing the spectral norms. Bound we're proving is k is at most L log n, where L is chosen to make the average degree of each of these matrices be at least 1. All right, so now let's go to the case of LCCs. So in the case of LCCs, remember, I'm given H1 through Hn. These are now 3 uniform matchings. And I do want to recall one fact from the slides part.
Sorry, is this including that extra guy or not?
No, not including,
forgot.
so it's 3.
That's a 4 query,
So it's a
it's a
3
3
query.
query LCC, the equation will have 4
4.
variables.
So what I want to recall is solutions to the system of a linear equation psi, which was, remember, it's like product b and c, xv is equal to xu, where all u and n, and then c in the hypergraph h sub u. This thing, I can identify solutions as indexed by some b and plus minus 1 to the k, where the bth solution restricted to its first k coordinates is b.
Yeah.
Okay, this was by like picking a basis property. Okay, and this means that within psi, I have the equations product of v and c, x sub v is equal to x sub I. This is for I and k, which is b sub I. This is for I and k. So secretly within these equations, I have one of these psi b instances that I had from before the LDC case. The difference here is I now have the extra n minus k matchings, which I'm going to use. Okay, so remember, we're going to prove a lower bound that's beyond the best LDC construction even. So I really got to make use of those matchings somehow. Okay, so let me show you what we're going to do. This is really the key part of the proof. Or rather, the reason we can get an exponential lower bound boils down to this one idea. And then the rest of the proof is all the technical execution to make it go through. But like there's one like big main idea here, which is that I'm going to derive new constraints. So that's the key idea. We're going to derive constraints. And we shall do it using the extra, I guess, k plus or n minus k matchings that we have. Okay. So I'm going to draw this as a picture. So I'm going to start out with a constraint that I'm going to write as, that's going to be too small. Okay. Try to make it big. Sorry. if it's
We do
not.
have like hundreds of views you do get on these videos.
I do. I do tell my wife's little brother-in-law that I'm a YouTube star. I send him my videos at the top of it.
And you've only just begun, you know?
Okay, so. Okay, so I can represent pictorially a constraint from before like this, where the condition is V1, V2, U1 forms a hyper edge in the hypergraph H sub I. Okay, so I'm drawing this picture, but there's a direction to it. Okay, this corresponds to the equation B sub I equals, well, B sub I is X sub I, but I'm going to write B sub I for the specific I, is XV1, XV2, XU1. Yeah. Okay, now here's what I'm going to do. I have a hypergraph for U1. So let's tack on another hyperedge, which is V3, V4, U2. So this now, what it adds is it adds an equation of the form XU1, XV3, XV4, XU2. Now, XU1 squares, it's in plus minus 1, so its square is 1, so I can just cross this out. And what I'm left with is that B sub I is XV1, XV2, XV3, XV4, XU2. Okay. Now, notice what I've done. The arity of my instance has gone up. It's now at 5. It used to be at 3, now it's at 5. On the other hand, I have produced more constraints. So let me write this. So the arity is 5. I'm going to let HI2 denote the set of the constraints given by this process. The 2 is because there's 2 hyper edges in it. And let's count the number of constraints here. So for the first hyper edge, I have delta n choices because that's the number of hyper edges I have. I do need to order the vertices the way I'm doing it. In particular, I really care about which vertex is in like the 3rd spot. So I'm going to pay a factor of 6 to order the vertices. That's just refactorial. Okay. So I have 6 delta n choices for the first hyper edge. And once I've told you the first hyper edge plus the ordering, I again have another 6 delta n choices here. So I get 6 delta n squared. Now I can go over to my heuristic. Let's see what we're going to get. Okay. So in the naive case, we had L was n to the 1/3 for q equals 3. This was n to the 1 minus 2 over q. Okay. Let's see what we get now. So maybe I should say this is before we had L as n to the 1 minus or n to the 1/3. Now we want the size of the hypergraph, which is about n squared. Maybe I should write 6 delta n squared times L over n to the arity, which is 5. It's odd, but I'm still going to do this anyways. I want this to be at least 1. Okay. There's an n squared, an n to the 5/2. I subtract, I get L to the 5/2 divided by n to the 1/2 should be at least 1. Or in other words, L should be about n to the 1/5. That's smaller. Okay, so this is predicting I'm going to get a bound of k is at most n to the 1/5. Still have to, go through a proof and make it work. But essentially, by the way, this heuristic is going to predict the actual lower bound we'll get with this whole approach if I'm able to find the subgraph B sub I within A sub I. So there's some technical stuff of showing B sub I exists, but other than that, this is what we're going to get.
And this is very different than just squaring the graph B sub I, because usually you won't follow like these 2 hyper edges. That you
B
just
sub I
said.
would be adding 2 hyper edges that
They're
have the same I,
independent.
that are in the same hypergraph
In the
I.
same I, but kind of not, they won't.
They also will not intersect at
not
all because there's a
cancel.
matching, so you can't even get anything that way.
Yeah, I was kind of worried that you're doing something, but it will
Yeah.
cancel because it's like squaring some matrix, but it's
No,
not.
this is really something different. And
I mean, it's slightly similar, but it's.
no, it's not really like squaring at all because the matchings there will not intersect. The
Yeah.
hyper edges will not intersect. I mean, intersecting is very important. You could do the thing for the odd case. What we actually do is we form like things like this where you had I and J. That's what we do for LDCs for the odd case, but this is a little bit different.
So you could do the same thing and just get
No.
some things that are arity 6 and you just wouldn't get an improvement, is that not?
Well, if you get arity 6, like, I mean, your hypergraph would go to size, delta n squared, but arity 6. I mean, it's the same hypergraph.
Yeah, that's-
You're not-
Yeah, that's when nothing would.
Yeah, you wouldn't get anything.
Yeah.
Another thing I want to point
Yeah,
out.
maybe pedagogically, I get that word.
Pedagogy.
It would have made sense to
Try that.
say that and then to say, oh, but now we make.
No, but you're not really
difference.
getting new constraints that way. Like here you're getting, like, okay, the important thing here is in the LDC case, I cannot do this. Because I take one hyper edge here, I try to continue, I do not have a hypergraph containing U
Yes, of
for-
course
for
you
you.
do.
for U1.
You do, because you have a lot of matchings. And by averaging,
There's a size delta K, not delta
right,
N.
but you do have this delta K that
Yeah.
you haven't used.
Yeah, but like, it's much smaller.
Not really smaller, K is polynomially named.
Yeah, but okay, you can do that derivation process and you stay at the end of the 1 minus 2 over Q threshold.
I mean, of course, I believe you, and I'm not.
No,
I'm
I've checked this code.
Suggesting I will do any calculation, I
Yeah.
just say that a priori, if I'm in some polynomial range and you have some observation that uses some
Okay.
polynomial edge, it could.
Sure, yeah, but then also the structure of this next edge will not be a matching either.
Well, you
That's-
don't have matchings here.
Yeah, I
either.
do. This
Do
this
you?
edge here, V3, V4, U2 is an edge in the hypergraph HU1.
No, all I wanted to say is that HI
Two is not a
parenthesis
matching.
two is uniform somewhat and so on, but it's not a matching like you had before.
No, it's not a matching, but it
So
does
you'll
have,
need to work harder now.
it does have a lot of matching like properties. Like if I told you V1, the number of hyper edges or the number of these, I call these chains or two chains that
Yeah.
look like this would be drawn by a factor of n, right? Whereas the other process that you described for LDCs does not have that property. And that's actually the barrier for odd Q. That was why it was so hard to get it to work. For odd Q LDCs, because you do this type of derivation process that you just wanted to do for LDCs. But then the resulting derived instance is not a matching, but it doesn't even look like smooth, the hypergraph.
Okay.
Yeah, and that causes a lot of problems.
Can imagine.
Okay, so I got a small gain going one step. What am I gonna do? I'm gonna do it a lot, okay? In fact, I'm gonna do it R times. And I mean, I can just do the computations. The arity that I'm gonna produce is I get 2 per hyper edge, but then the last guy has 3 things. So the arity is 2R plus 1. By the way, you should notice this is always odd. Okay. Which is unfortunate. We would have liked it to be even, but sadly, it is not. It is odd. Okay, the number of chains I get of length R is some 6 delta n to the R. So I can go over here and try to do my calculation again and see what it gets. I can put it in R, I can put in my arity, which is 2R plus 1. And what you basically get is that this n to the R cancels with the n, well, there's an n to the R over half. So I still get an n to the 1/2, but now I get something that's like L to the R over here. This is an absolutely massive one. So this says that I should really maybe take L to be constant and R to be log n, but L always has to be at least the arity of the instance divided by 2. So L has to be at least R, which we're going to take to be log n. Okay, now what's my predicted lower bound? My predicted lower bound here is K is at most L log n, which is log squared, which is optimal. Okay, read molar codes achieve this. So this is saying that we have a method that can potentially get us all the way down to log squared n. Now, the main technical difficulty is you will take this thing,
Mhm.
you will convert it into a graph. Now it's odd, so I can't do it exactly the way I've been describing things so far, but you can do a related version of it.
Mhm.
And the real question boils down to, can you find this approximately regular subgraph?
Mhm.
And this gets complicated because what that boils down to is counting the number of chains where I like tell you certain variables. Like let's say I tell you that V3 is some fixed vertex and V2 is some fixed vertex. And now I ask you to count the number of chains that start at I, have V2 being some fixed thing and V3 being some fixed thing. Okay, I want you to count that. This one is easy to do. You can say, I know V2, it's a matching, so this determines this hyper edge here. I go here, I know U1, I know V3, it's a matching, it determines this edge here. Then here I hit U2, I don't know anything else, so I just pay like a 6 delta n to keep going. So you can do calculations like this, but the issue comes when I tell you 2 vertices in the last hyper edge. So each hyper edge has 2 vertices in it, and the last one has 3. So that means the way I'll split it across row and column is each row will have like 1 per link. Except the last guy I have to put its 2 vertices in somewhere. So 2 of them will be on one side of the graph. And that means I need to essentially count the number of chains that end in some specific pair of vertices. And the thing is, I need it to drop by like a factor of n squared, not just n. And the thing is, if I try to count the way of just like walking forwards like this, I will hit here and only lose a factor of n. So what I need is that this pair of vertices appears in maybe at most a constant number of hypergraphs h sub u across all the n matchings. This is not an assumption that I can make. So this is not in general true.
But you have it in the Hamada.
Yes, in the design case, you do have it. That's why in the design case, we get the nice log squared bound. The matchings are also perfect. That will lose us another log factor when they're not perfect. It's because the 6 delta n is like really 3 delta. The 6 is there's a 3 choice for the last vertex, and the ordering of the 2 in the middle doesn't actually matter. And the thing is, there's a 3 delta here. When the matchings are perfect, 3 delta is 1. And when they're imperfect, it's less than 1. And that loses something else. Okay, but those are kind of the 2 barriers. So it turns out this is not going to actually satisfy the approximate regularity condition. There's more work that needs to be done. We need to analyze like if there is a problem with this sort of decomposition step here, or the subgraph step here. We need to figure out what the combinatorial structure is in these chains that's causing this to fail, and figure out a new way to make a better matrix to get the refutation to work. And then this is losing us a log factor because of the pairs and a log factor because of the perfect matchings. And so we end up at log to the 4n for the general case. But in the design case, we don't have these extra conditions, and then we end up at the log squared. Okay. Oh yeah, well, we're way over time. Okay.
Okay, bravo. You want to ask more questions, or should we ask you on the way to that? What about the 5 query LCC, 4 query LCC?
Yeah, so what you can do is, if you view this as a reduction from, you can view our proof as giving us a reduction from a 3 LCC to a 2 LDC, where we go from length n to length n to the log n, or n to the polylog n.
Okay,
And then you apply the 2 LDC lower bound, and you get k as at most log of n to the polylog, which is polylog times.
what?
Okay.
So, okay, maybe I don't want to.
You don't want to ask, okay.
No, I want to ask, but maybe I don't want everyone to have to
Okay.
be hungry and listen. I don't know.
I mean, basically, you can view the proof as like a 3 LDC, or 3 LCC gives us a 2 LDC.
Why? What's the reduction? I
So
didn't see a reduction.
The reduction is the matrix has 2 sides, a row and a column, and then those are like your 2 queries.
What matrix you're
So when I haven't told you the matrix, I haven't. But like this matrix A sub I, see if I look at this matrix A sub I can now recover B sub I with 2 queries. I query a row and a column that have an edge in A sub I. And when I add those 2 things together, I will get B sub I. So you could view these things as giving some sorts of reduction. So we're basically giving a reduction from a 3 LCC to a 2 LDC, or 4 LCC.
Can you describe it in the semantic world? What's the reduction from a 3 query LCC to 2 query LDC?
Yeah, so you start with the 3 query loop. I give you a new code. So this, let's say, has dimension k and length n. I produce a new 2 LDC with dimension k and length maybe n to the log n. And so this means I can then bound k using the 2 LDC lower bound.
What's this new into the log n? You have a bit for every.
The log n to the log n is the size of the matrix. So this is like n choose L.
Ah.
Yeah.
Okay, now I see.
Nice.
Okay. So you have a new bit in your encoding for every L bit in the old encoding.
Yeah.
Mm. Cool, okay.
Yeah, and then you can do this for larger queries. For complicated reasons, you can make this, well, actually not for so complicated reasons, but when Q is odd, then you have an even number in each of these hyper edges. So that's actually the good case for us. So for odd Q, I can get the Q LCC to a Q minus 1 LDC reduction. But with a like a log and the exponent blow up, which is not enough to do anything, but if you were to analyze it directly, you would get an improvement here. You basically plug in, you get n to the 1 minus 2 over q minus 1. is what you would need. Which is Q going to Q minus. And for Q equals 2, you go from 3 to 2, where 2 we have an exponential lower bound, which is why we get such a good lower.
Okay, fantastic.